Hello, this paper presents the application of current limiting inductance effect on Class E driver circuit for inductive wireless power transfer. The authors of this paper are Mohammed Karam Moni Rabby, Shamim Ara Shawkat, and Mohammed Shah Alam. This research was conducted at Bangladesh University of Engineering and Technology, in short called BUET, Bangladesh, in collaboration with the University of Tennessee, USA. I will walk you through our work in the following order. First, a brief overview of inductive wireless power transfer, in short called WPT. Then, the background and key applications that motivate this research. We'll discuss the advantages and inherent challenges, leading to our specific focus on voltage regulation. I'll then show our system block diagram, explain our step-by-step design technique, present the simulation results, and finally share our conclusions. At its core, inductive WPT is based on the principle of electromagnetic induction. An alternating current in a primary, or transmitter, coil creates a varying magnetic field. This field induces a voltage in a secondary, or receiver, coil, which can then power a load. Our research focuses on optimizing the electronic driver circuit that powers this primary coil. The visionary Nikola Tesla demonstrated the possibility of wireless power over a century ago. While his large-scale dreams were ahead of their time, the principle lives on in modern, short-range applications. Our work builds upon this legacy, aiming to solve practical challenges in efficient, small-scale power transfer. WPT is crucial where wires are impossible or inconvenient. A key application area is biomedical devices, such as pacemakers, cochlear implants, and endoscopic capsules, where it eliminates the need for percutaneous wires and reduces infection risk. Beyond medical use, it's enabling convenient charging for consumer electronics, electric vehicles, and industrial sensors, driving the need for more efficient and reliable systems. The benefits are clear: enhanced reliability by eliminating connectors that can fail, greater user convenience with automatic charging, and environmental benefits through reduced battery waste. These advantages are what make solving the technical challenges so valuable. Despite its promise, WPT faces significant hurdles, maintaining high efficiency over distance and alignment, product-specific optimization, and regulatory issues. Our research specifically targets the challenge of providing stable, regulated voltage to the remote load, which is critical for powering sensitive electronics like sensors and microcontrollers, regardless of coupling variations. This is the high-level block diagram of our proposed system. A DC source feeds a Class E driver via a current-limiting inductor, or choke coil. The driver excites the primary inductor, which wirelessly transfers power to the secondary. The received AC is then rectified and filtered to produce a stable DC output for the load. The circuit diagram below shows our implementation, highlighting the key components we will design: the choke coil, L_choke, the Class E network, C1 PAR, C1 SIR, LS1, and the secondary resonant tank. Our design methodology is a two-stage, iterative process. First, the magnetic design defines the coil geometry and coupling based on physical constraints and power demands. Second, the electronic design uses these magnetic parameters to calculate component values. We design the secondary circuit first, then the primary circuit including the critical Class E driver and the current-limiting choke coil. The process is validated through simulation until performance targets are met. This flowchart details the secondary circuit design. We start from the load's power demand to calculate an equivalent AC resistance. We then select a secondary coil, LS2, and a matching capacitor, C2, to resonate at the operating frequency, maximizing power transfer efficiency. The quality factor Q of the coil is measured and used in an iterative process to finalize the component values that achieve the target link efficiency. With the secondary designed, we now design the primary. We calculate the required primary inductance, LS1, and the Class E driver components, C1 SIR and C1 PAR, based on the reflected load from the secondary. A key step is evaluating the driver efficiency and switch stresses for different primary coil options. We then select the coil with the highest quality factor. The design is finalized and verified with a SPICE transient simulation, ensuring the driver operates correctly with ZVS. This is a key contribution of our paper, optimizing the choke coil, L_choke. Conventionally, for megahertz frequencies, a value near 1000 H is used. We propose a scaled selection method. Our analysis shows that for optimum current flow and to achieve zero voltage switching, L_choke should be chosen relative to the source voltage. We derived a relation where a lower inductance than the conventional value can improve performance, especially at 50% or higher duty cycles, by reducing impedance and increasing primary current during the switch-off state. To validate our design, we defined a specific test case, powering a small telemetry unit requiring 5.5 V at 5 mA over a distance of 70 mm. Using our design procedure, we calculated all component values shown here in Table I of the paper. We implemented the circuit in SPICE using a single, low RDS, on MOSFET. The simulation commands are set for a 1 MHz frequency with a 50% duty cycle pulse. The simulation results successfully meet our design target. We achieved a low DC voltage of 5.75 V and a current of 5.23 mA, exceeding the 5.5 V requirement. The quality of the output is excellent, with a very low ripple factor of 1.56% and a form factor of 99.99%, indicating a stable, clean DC supply. The graphs on the right, from figures 4 and 5 of the paper, show the steady voltage and current waveforms delivered to the remote load. In conclusion, we have presented an optimized Class E driver design for inductive WPT. By refining the selection of the current limiting choke inductor, our circuit reliably provides a stable, regulated voltage higher than the source to a remote unit. This addresses a key challenge in WPT systems. Future work will focus on further improving overall system efficiency and developing coordination methods for voltage regulation under varying coupling conditions. Our work builds upon foundational texts and prior research in inductive powering and efficient driver design, notably the work by Van Schulenburg and Puers, and studies on Class E amplifiers and loosely coupled systems from IEEE literature. The development of the application of current limiting inductance effect on Class E driver circuit for inductive wireless power transfer is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.